this research question using your data. Okay, let me see. Something is on. Okay. So this could be a research question, right? You want to understand whether the average body temperature for healthy adults from your region, right, is different from 98.6 or not. This is 98.6 is kind of standard that used for years. And probably your clinics or you've been in the hospital and you're doing the physical check for people and you realize that body temperature for healthy adults oftentimes not 98.6 and even below that. So you want to figure out why is that, right? Is it true that now actually is different than 98.6? Okay, so what you will do, from the region that you lived, or maybe northeastern Ohio, right? There are hundreds of thousands of people. You take a random sample of certain size. Here I have like a 12 piece of data. So I got different numbers, right? And I want to use these numbers to help me to answer the question whether the average body temperature is different from 98.6 or not. Okay, so I got to go through the hypothesis testing procedure for testing this hypothesis research question, whether the average body temperature is really different from 98.6. Okay. Okay, so what I do, well, I get a sample mean, and actually average is 98.31. Wow, that's actually kind of interesting, right? It's really less than 98.6, so it's different. But is that difference statistically significant enough? Okay. Could it be that next time I take a sample size 12 and I got a 98.8, right? So I don't want this to happen just, because of the coincidence, right? Just that small, next time I have large, and so this evidence is not going to tell me anything, right? So I want to see whether this evidence is strong enough statistically, significant enough or not, right? So we're going to make use of this sample mean and also the sample standard deviation to help us to figure it out. Right? So before we do any statistical hypothesis testing, right, these are the things that we certainly would do always, right, procedure-wise, while you're going through this test procedure, right? You first always have to state two statistical hypotheses, right? One null, one alternative. Okay, then use these test statistics to draw your conclusion about these hypotheses and so what's the null hypothesis? Here we look at the slide, right? Here, when you're doing any kind of testing, the null hypothesis usually relate to no difference or no relation, right? When there's no difference, if you try to compare some descriptive measure, parameters like mean, right, or proportion of a distribution, right? You want to see this mean of a distribution like this particular problem, average temperature is 98.6 or not, right? And null hypothesis will be no different from 98.6. Right? Now, if you try to study correlation between variables, and you may say null hypothesis, there's no correlation, right? So that's typically the null hypothesis. So in your null hypothesis, if you want to use a math expression to display your null hypothesis when you try to compare with certain value, you always have an equal sign in there, either strictly equal or greater than or equal or less than or equal, right? So for testing whether the mean body temperature is 98.6 or not, you can say, well, null hypothesis mean equal to 98.6, right? Equal sign in there. Or you can just write a statement, average body temperature is 98.6. That is null hypothesis, okay? Then you will have to also set another hypothesis called alternative hypothesis. And that is the hypothesis opposite to your null hypothesis. Okay, and oftentimes is the reason that you want to do research, right? So in that case, opposite to that would be what? Greater than, strictly greater than, right? And there's no equal in there, right? Strictly greater than, strictly less than, or not equal to. So it depends on what null hypothesis is, right? Or alternative hypothesis is, okay? There are different kind of testing rule that we use, right? So first of all, here, we could have an alternative hypothesis that the opposite to null hypothesis, that is the mean is not 98.6. So by notation, you can write this notation, mu not equal to 98.6. That's alternative, right? Your null hypothesis always have equal in there. And for me, I always use the equal sign. I don't bother with greater than or less than equal. Right? I just use equal, okay? And of course, you can also write a sentence like that. Average body temperature is not 98.6. That could be an alternative hypothesis, right? So that's just one possible alternative hypothesis. It depends on the research question. So here I have some examples. This first example, right? If we have this research question, how do we set up our hypothesis? Now, what's null, what's alternative? So if you want to find out whether average hourly salary for babysitting in this area is different from $10 per hour or not, okay? So $10 is the number you're comparing with. The null hypothesis always hypothesis of no difference. You're going to say, well, mean is 10, equal to 10. That's null, all right? And the alternative will be not equal to. That's what your research question is about, right? Is it different from $10? Okay. When you have this kind of set of hypotheses, null and alternative, usually the kind of test you use, we call it two-tailed test, right? Why this two-tailed test? Well, you want to see whether the mean is different from 10 or not. So you want to, once you collect the evidence, let's say you get a sample mean average hour salary, and you found this average hour salary is significantly less than 10 or significantly greater than 10, right? Either side would lead you to reject the null and support the alternative, right? So later on, when we review about making decision, usually we will say, we will draw some lines on the left side or right side of the value 10 to determine whether your evidence is strong enough or not. That's why we call this two-tailed test, right? When we review the actual test, you will realize that, right? So that's one possible pair alternative. Now, it could be that you're doing research question testing whether the average lifetime for male is higher than 77 years or not, right, for a certain population. So if that's the case, you have a number, 77 again, right? You want to compare with that number, testing that number. So null is, the mean is 77. Null always a hypothesis that your mean equal to a certain number. And the alternative reflecting higher than 77, okay? Now, some people actually, when you have situations strictly greater than 77, then you set your null is less than or equal to 77. Some people do that. That's fine, right? But as long as you have an equal sign there, that's good, okay? Anytime you have an equal, you want to put it in null. You have strictly greater than, strictly less than, or not equal to. You want to set it as alternative, right? So when you have a situation like this, we're going to say test for this is called right-tailed test, and you will see that later, again, the reasoning, right? Typically, when you have a situation like this, if you have a sample mean that's much larger than 77, more likely you will reject null and support the alternative. You're going to say your evidence support the alternative, right? And you will draw a line on the right side of 77. So if you have a sample mean greater than that value, then it's going to say your evidence support the alternative and reject null hypothesis. So that's right tail where you're making a decision on the right tail. Okay. So a pair of hypotheses like this, we're going to say that you're going to have a right tail test, right? Now, there may be a situation like this, right? You want to find out that average regular gasoline price is less than $3 in Midwest region or not. Okay. So you take a random sample and you can test this, right? And null hypothesis will be average is $3, right? Then alternative, that's what you want to test, less than $3. So that's the alternative. Okay. And of course, in this situation, you can make your null hypothesis greater than or equal to. As long as they're equal, that's fine. But that's strictly less than should be in the alternative hypothesis. Okay. So before you do the test for mean, you got to have these hypotheses set up, null and alternative. You have to set up that. That's the first step, right? Converting your or transforming your research question into statistical hypothesis testing, hypothesis, I should say. Okay. And of course, this is a left-sided test, right? If you have value that is much less than 3, you're going to say, well, evidence support the alternative. Okay. Less than is on the left side, right? The decision criteria on the left side. Okay. So that's very important. Before you actually do a test, right, you got to write these hypotheses down properly, correctly, right? Sometimes you want to do less than, sometimes you want to do greater. It depends on the research question. And I'm going to use a z-test, just like when I can explain the confidence interval, use a z-score. I'm going to use a z-test to explain test for mean, all right? Since we know that this normal distribution very well, okay? And we have a normal distribution that actually standard normal table gives us a lot of detailed distribution. All right, so I'm going to explain the concept using the z-test. Okay, and so this is the first thing you will do, right? If I have a research question that is want to test whether average body temperature for healthy adult is less than 98.6 or not, if that's what I want to test, okay, then the null hypothesis will be equal to 98.6. Alternative is less than 98.6, right? So that has to be done first, okay? And since I'm testing mean, so sample mean is the best number for studying population mean, okay? So I collected a random sample of 36, and I found the sample mean is 98.46, and standard deviation is 0.3. So 98.46 is kind of less than 98.6, but is it evident strong enough? Well, I'm going to see. How do I test this hypothesis? And this is similar to all hypothesis testing procedure. While you're testing this hypothesis, first you want to assume that this null hypothesis is true. The null hypothesis, if we say mean is 98.6, right? So we first assume null hypothesis is true. So if null hypothesis is true, what's the sampling distribution of mean? What's the probability distribution of sample mean? Well, first of all, we know it's normal if the body temperature data is normal, right? The population of those body temperature measure is normal. And you can check normality, right? And the data I have at 36, usually they say that's large sample. Large sample is large enough, so I can say sample mean is normal. So anyway, I know that sampling distribution of mean is normal. And also, if I say null hypothesis is true, then the mean of this distribution is 98.6, okay? And the standard deviation, I don't know it, but I know the standard deviation of sample. I'm going to use that to estimate it. So I use the standard deviation sample divided by square root of sample size. I got the standard deviation for the sampling distributed mean. All right? So I have the probability distribution of sample mean now. This is under null hypothesis when null hypothesis is true. Okay? And this is actually the logic behind hypothesis testing, right, for mean, and actually for all the hypothesis testing. We first assume null hypothesis is true. Then we'll try to look at the evidence, evaluate the evidence to see whether the evidence is extreme. Is an extreme case or not under null hypothesis, right? If evidence is extreme case, then you're going to reject the null hypothesis, right? If evidence is not extreme, it's easy to see in the null distribution, then we're going to say not rejecting null hypothesis, right? So how do we measure the extremeness of that evidence? Since we assume null hypothesis is true, the mean of a distribution is 98.6. Standard deviation of the sampling distribution is 0.3 divided by 36, square root of 36. So I standardize my evidence using the mean and standard deviation. I get a value that is negative 2.8. So I hope you understand this meaning, the z-score, okay? Z-score tells you how many standard deviation is your data away from the mean of a distribution. And this is mean under null hypothesis, okay? It is negative 2.8. Your knowledge about normal distribution, 2.8 standard deviation from a mean, is extreme, right? It's in the tail, okay? And it's actually negative 2.8 is in the left tail, okay? So I draw a standard normal curve because this now I'm kind of just helping to understand actually how extreme the negative 2.8 is. Negative 2.8 is actually very extreme. There's almost nothing to the left of negative 2.8, right? But we got to make decision, right? We see negative 2.8. Is that extreme enough, right? Generally, we're going to use a cutoff point. We call it critical value to help us make decision, right? If your evidence passes the cutoff point to the left, in this case, you're going to say we reject null hypothesis. How do we decide this cutoff point? It's based on the level of significance of the test. We call it alpha, okay? If your evidence so extreme lies in the tail alpha proportional distribution, and we say the evidence is extreme, we're going to reject the null hypothesis, right? So for that case, if I have specimen alpha, that's 5%, that's commonly used level, then I will use that 5% to figure the cutoff so that the distribution to the left of that cutoff is 5%, okay? So I would know my evidence is in the tail 5% of distribution or not, okay? Now, so actually, for this particular case, if we use 5%, and from a standard normal distribution, if you want to find a cutoff, that left tail is 5%. That score is actually negative 1.64 if you look up the standard normal table. Okay, and our evidence is negative 2.8, so it's in that region. So evidence is in the tail 5% of a distribution. I'm going to say I'm going to reject the null hypothesis. Okay, so that's so-called a critical value approach, and the rejection region set on the decision criterion set on the left tail, so we call this kind of test left-sided test. That's the reason why we call it left-sided test, right? That critical value is on the left side. Decision-making really depends on the behavior on the left side of the distribution, right? Whether your evidence is extreme and extremely to the left or not, okay? So that's critical value approach, but people don't use this. This is actually an approach that's easy for us to learn the idea, okay? Now, the approach that people use in practice is actually called p-value approach, right? P-value is what? P-value is the probability, when null hypothesis is true, the probability of observing an evidence, right, that is as extreme or more extreme, right, than what you observed. Extreme in the sense that it will reject the null and support the alternative. So from the left-sided test, we actually look for area to the left of negative 2.8. That's a p-value. So if you look at a table, Z table for area to the left of negative 2.8, it's about 0.003, about 0.0026, I think, if you use 4 decimal place table, right? So that's a p-value. Remember, you do p-value approach for normality test. Your conclusion is if p-value less than 0.05, you reject the normality, right? Because back then, the null hypothesis is normality. Alternative is non-normality, okay? Over here, your null hypothesis is that mean is 98.6. Alternative is the mean is less than 98.6. Now, if you have a p-value so small, you're going to reject the null and support the alternative that mean value actually is less than 98.6, okay? And this is the approach that everybody uses. Nobody uses critical value approach, right? Critical value approach is good for some other purpose, right? But definitely when you report, usually when you report that result from testing hypothesis like this, you don't do that, right? So once you've done that, especially in your homework assignment, I'd like you to write some conclusion like this. Oftentimes students just say, I reject the null hypothesis, and they stop it there, okay? Rejecting the null hypothesis doesn't say anything. You want to explain to people what's happening, right? So if you reject null hypothesis, that means there is sufficient evidence to support the alternative that the average body temperature is less than 98.6, right? And usually we say this evidence is statistically significant, right? Because you perform a statistical test, right? And realize that statistically, from the data, right, it suggests that the average is less than 98.6, okay? Hope that makes sense, right? So that's the, and you see when I do this, I actually went through several steps, right? I first state hypothesis, null and alternative. Then what I do, I compute that test statistic, z-score, okay? Then I should define a decision criteria. And usually people use an alpha, 5% level of significance. Okay, students are often confused with confidence interval and hypothesis testing. When you do confidence interval, you say 95% confidence level. When you do hypothesis testing, you're going to use that level of significance alpha, and that alpha usually is 5%. Some people use 1%, right? Some people use 2%, and most of the time people use 5%, right? So that's decision criteria you use. So this helps us decide whether you reject null hypothesis or not. If you set it at 5%, I'm going to say, I will reject null hypothesis with when p-value is less than 5% or 0.05, right? So you have decided that, then you can use that with the p-value you get from the test statistic, you make decision, right? You reject null hypothesis if p-value less than that alpha. And of course, after that, you also want to conclude about your alternative hypothesis, right? Make sure you always, when you do your assignment, make sure you always write this statement, a statement like this, right? Saying what your evidence support or do not support the alternative hypothesis, right? The language is like this. When it comes to null hypothesis, you always say reject or not rejecting null hypothesis. When it comes to concluding about alternative hypothesis, you always say your evidence support or do not support alternative hypothesis, right? Not rejecting null hypothesis, that doesn't mean null hypothesis is true. So you don't say you accept null hypothesis, don't say that, right? Just say reject or not reject null hypothesis. And say support or not support alternative hypothesis. Okay. This whole process is like a judicial system, right? When a person is a criminal or a person is on trial, you first assume this person is innocent, right? That's like null hypothesis. So you start collecting evidence, right, to see whether this person is guilty or not. If the evidence is strong enough, right, then to a certain level, then you're going to say this person, you're going to say the evidence support that this person is guilty, okay. And that doesn't mean if you don't support the person is guilty, that doesn't mean this person is really innocent. Okay, it's just you don't have enough evidence to support that the person is guilty. Right? So this idea is similar to that. Right? Now this graph is just if you do p-value approach, the rule is like this. If you do right-sided test, right, p-value will be area to the right of the test statistic. Like for this example. If you're doing a right-sided test, testing whether the average body temperature is greater than 98.6 or not, p-value actually is to the area to the right of this. That'll be 0.997, right? We're doing a left-sided test, so p-value is the area to the left of this, so it's 0.003. Okay. Now, if you're doing two-sided tests, remember p-value is a chance of observing evidence that's as extreme or more extreme than the one you actually observe. If you're doing two-sided tests, testing whether it's different, mean it's different from 98.6 or not, then if you found an evidence that has a z-score 2.8, that evidence has the same extremeness as negative 2.8, right? Okay? So actually, if you do two-sided tests, you want to double this tail area. So your two-sided test p-value will be twice of the tail area. That's why I use a notation like this. Okay. One-sided test, area to that, whatever side you're testing. You're testing right-sided test, area to the right. You're doing left-sided test, area to the left of your test statistic is the p-value, right? If you're doing two-sided tests, just look at that smaller tail. Your statistic cut the distribution into two parts, right? Look at that smaller tail multiplied by 2, you get the p-value, okay? So here it's just what I just said, okay? Now there's some possible error when you're doing hypothesis testing. One is called a type 1 error. Type 1 error is that when null hypothesis is true, but you rejected it, okay? It's possible, okay? You do a hypothesis testing, and null hypothesis is true, the average body temperature is really 98.6, no different from 98.6, but unfortunately, the sample that you gather just happened to give you a number that is so small, so you reject the null hypothesis, and so you make a mistake, right? And what's the chance of that? If you specify alpha level as a critical value, right, that's really the probability of committing type 1 error, making mistake, right? The distribution, null hypothesis is true, but you just end up having a number that's so extreme, okay? That chance is actually also the probability of committing type 1 error. And that's also tell us why, a lot of people always use 5% or 1% as a critical value, as a level of significance. They don't want to use 20% or 30%. If you use 20% or 30%, you're more likely to reject null hypothesis, right? But it's also means that you have a higher possibility of committing type 1 error, committing error. That's not what you want to do, right? So after years of practicing, people rather think 5% is reasonable. Similar reason as that 95% confident, right? But remember that 95% is for confidence estimation, confidence interval estimation. This 5% here is for testing hypothesis. So be careful in your language, right? When you're trying to state significance of a test, right? Or commenting on confidence interval estimation. There's another type of error called type 2 error. That's when null hypothesis is not true, but you did not reject it, right? Or the alternative hypothesis is true, right? But you did not accept it, right? Or you actually make the other decision. That's type 2 error. This type of error is related to actually sample size calculation. When we do hypothesis testing, we would mention that if we have time today, okay? So this is just telling you, this slide is just telling you, when you do hypothesis testing, you have to have a research question first, okay? And stay with that research question from the beginning to the end. You don't want to look at the data and then change your hypothesis so that your data actually will meet, the outcome will meet your goal, right? That's not right, right? That's actually, you introduce a lot of bias in there. So a proper hypothesis testing procedure is that you have the hypothesis set up, okay? Then you go gather the data, right? And then you do the hypothesis testing, okay? And don't change the hypothesis, okay? Good. So that's an example for using standard normal distribution for doing the test. However, again, in practice, just like confidence interval estimate, nobody really uses a z-test for similar reason as a confidence interval estimate, right, with a t-score. Right? So here is an example for t-test, how we do a t-test. Right? Again, it's because when we try to standardize sample mean, using the estimate for standard deviation, especially when sample size is small, this quantity don't follow standard normal distribution anymore. It follows a t-distribution with degrees of freedom n-1. Right? Fisher derived that formula and result in the distribution. Right? So we're gonna talk about this. Okay, same kind of setting. When you do hypothesis, let's say we're going to do the same testing. Okay, and I'm going to assume my sample size is smaller. Right? So I got to check normality assumption. I have a sample size 16. And they give me a mean, same thing as we saw earlier. And this time I have a sample standard deviation of 0.2. That's from the data that I observed. I use that to estimate standard deviation. So for standardizing 98.46, what my sample mean that I observed, I subtract the mean under null hypothesis divided by standard error. Now, I made this up, so the outcome still negative 2.8, okay? But this time is different. When you have this situation, right, this statistic actually follow a t-distribution now, okay? A better way to do it is use a t-distribution, okay? And since the sample size is 16, so degrees of it is 15, right? So we're going to use the degrees of 15 to do the problem. I have a z-score, test statistic score, negative 2.8. It's on the left side, right? So what I need to do, if I want to take critical value approach, I got to find a t-score so that the tail area from this t-distribution is actually closer to this, so I can actually estimate this. Because unfortunately, when you have a t-table give you very limited information. They only give you some specific tail area. So what I can find is at least what kind of t-score, if I do the critical value, what kind of t-score will give me tail area 0.05 to make decision using critical value approach. So I look up a t-table for tail area 0.05 with degrees of freedom 15, okay? I get actually a t-score 1.753. Let's look at this, right? 0.05 degrees of freedom 15, 1.753. This is right tail. Okay. Now you know the t-distribution is similar to standard normal, right? If you have a right tail 5% area with a t-score 1.753, then if you want to find a t-score that left tail is 5%, that t-score is negative 1.753. So with that table, you'll be able to find the cutoff in the left tail. This is a critical value approach. If you want to find a critical value such that tail area is 5%, right? You can use a t-table to do that. Okay. But if you want to do p-value approach, you got to figure out the area to the left of negative 2.8. That's a probability of observing evidence as extreme or more extreme than the one you actually observe, right? It's hard with a table to figure out this tail area. But fortunately, we have computer software able to help us to do that, right? We have Excel. If you use a t-distribution, it will give you the tail area. So if you do the homework, sometimes you may have a question like that, right? Now, if we use a table, what you can do is actually find some t-score that is closer to 2.8, right? To see what kind of tail area it has to help you to approximate it, right? I found a number that's closer to 2.8, that is 2.6. Its tail area is 0.01, so I know the tail area for 2.8 is definitely less than 0.01. And less than 0.01 is less than 0.05, right? So I will reject the null hypothesis because of that. Okay. So the same way I can draw my conclusion. Okay. Since use the critical value, I have a t-score that's less than critical value is in the rejection region, or use a p-value. My p-value is less than 0.01, definitely less than 0.05. I reject the null hypothesis, or I draw a conclusion. So that's how you perform a t-test. Okay. So again, you will have to state hypothesis, null, and alternative, and you have to compute the test statistic. The formula is the same as that z-test, it's exactly the same, except for now I gotta use a t-distribution instead of using a standard normal. Okay. And an important assumption we need to check is normality. When the sample size is small, you want to check normality. If the sample size is small and data is not normal, this t-test doesn't work. Okay. There are other methods to do, okay, but t-test won't work in that situation. Now, that some people have done some simulation in the past realize that, well, when you have slight deviation from normality, t-test is still pretty powerful. So usually, if your data is not too deviate from normality, you get a p-value it's less than 0.05, but not too far away from 0.05. People still use the t-test to do the test. Okay. So I hope that makes sense, right? Okay. So if instead I want to do actually two-sided tests, want to test whether the average body temperature is different from 98.6 or not, what do I do then? I would just double this tail area. Okay. So if one tail is less than 0.01 and two tail to be less than 0.02, and that should be my answer. Okay. Yes?
Hey, I got a call from Amy.
Mm-hmm.
Is that
Yeah, the technician just came up and asked something. Okay, so we're fine. Okay, so for t-test, right, the way you calculate the p-value is the same thing, right? If you're doing a left-sided test, you'll find the area to the left of a test statistic. That's a p-value, right? For right-sided test, you'll find the area to the right of the test statistic. Okay, like this one. Left-sided test, I need the area to the left, right? Right-sided test, I will have the area to the right, and of course, area to the right of this will be greater than 0.99, right? If left of it is less than 0.01, to the right is greater than 0.99, so you know it's definitely greater than 0.05. If it's two-sided test, it will double the tail area. Okay, so that's how you figure out p-value for the test. Okay, so again, when do we use t-test? The condition is the same as a confidence interval estimation. Okay, if you have large sample, use t-test. When you have small sample, you can use t-test, but you want to check normality. So the same assumption you use, right, for confidence interval estimation. Right? When you do have large sample, that interval estimation you learn is good. When sample size is small, check normality just to be sure. Right? Now, when the data is not normal, some people, like I said, some people claim that I've done some simulation. I think I did some in the past too, and t-test is somewhat robust against normality. That means if data is not quite normal, t-test still work pretty well. Right? But if the data is really, really skewed, then you should choose something else. And there's a non-parametric test called sign rank test that we will learn later on in the class that will actually take care of that problem. Okay, so you can use that instead of t-test. Okay, this is that same example that I mentioned earlier, right? We estimate the average weight. Right? This time we want to test hypothesis whether average weight is greater than 78 pounds or not. If this is the research question, I have my sample mean and standard deviation like that, and I can use 5% level of significance to test this hypothesis, right? So how do we do that? Null will be what? Mean is 78. Alternative is mean greater than 78, right? That would be your alternative hypothesis. Then what we do? Compute the test statistic. Standardize your sample mean 80, subtract the mean under null hypothesis 78, divide by standard error. Okay. Now that standard error is what? Standard deviation divided by square root of sample size. So that's 5.71. So that's in the denominator. Okay. And if I actually change the sample size to 400, okay, that actually would change the standard error. If the standard deviation doesn't change so much, right, but sample size changed to 400, that will actually make my standard deviation or standard error so small. Okay, you see how that affects the t-score. Okay, with a small sample size 10 and large sample size 47. With small sample size 10, this denominator only 5.7, right? Now numerator is 2 point something, right? 80 minus 78 is 2 point something. Denominator is 5 point something. So then that t-score is less than 1. If a t-score less than 1, that means it has a large tail area. The p-value is definitely greater than 0.05. But if your sample size is 400, your standard error becomes 0.9, right? So 2 divided by 0.9, you get a t-score that is greater than 2. That more likely to indicate that there is a significant difference, right? So this kind of helps you to understand actually the sample size will affect the result. If you want to do hypothesis testing using a very large sample, very likely you're going to reject null hypothesis. Right? Years ago, there was a physician tried to do some research in the hospital, and he collected a few 100,000 data and want to test hypothesis. He said, every time I test hypothesis for mean for different variable, it always reject. Wow, what a surprise. I said, of course, that's not a surprise because you have really large data. When you have really large data, your standard error becomes very small. So you always get very large t-score. You always reject null hypothesis, right? Now, when we do these hypothesis testing, usually we do that for limited sample. When the sample size is small, okay, you do hypothesis testing to understand the statistical significance difference, right, for the parameter to some hypothesis value. If you have really large sample, the descriptive statistic itself will be good enough. You don't really have to do hypothesis testing. Okay, I hope that makes sense, right? So this example kind of help you to understand sample size actually affect the result. Sample size get large, your test will be more likely to detect the difference, and you more likely reject null hypothesis. right? So when you do drug development, you ask 1 million people to participate in your drug treatment and study, then very likely you're going to see some difference, right? But unfortunately, that's not going to happen. When you're developing drug, right, it's something that will hurt human subject, right, when they participate in your subject. So usually you have this very small sample. You have 10, 20, 30 people, right, 50 people. So that's small sample. And from there, you're going to use a t-test for helping you to draw the conclusion. Okay. So you realize sample size actually matter, right? And if you're doing a medical research and try to understand, evaluate a particular treatment, you know that you can actually go on and get so many people to involve in your study. If you're asking for a grant especially, people will ask you to justify why you need that many data, right? Why you need that many people. So how do you do that then? You have to justify for your sample size. That comes to the sample size issue, right? How do we determine sample size? Okay, so that's the last set of formula I'm going to mention, right? How do we define sample size? We mentioned type 1 error rate. That's the alpha we use for making decision, right? Now there is a beta, which is probably a committing type 2 error, right? Type 1 error is reject null hypothesis when it's true, right? And type 2 error is accept null hypothesis when it's not true, right? Or reject the alternative when it is true, something like that, okay? And when we do hypothesis testing, evaluating the procedure, we have so-called the power of a test, right? Related to sample size, in fact, is power of a test. Okay, of course, also depends on our alternative hypothesis and null hypothesis you set up. Okay, but the power of a test generally is defined by probability of beta. In fact, probability of beta is probably a committing type 2 error, right? 1 minus beta, we call it power of a test. Okay, so that's how we define the power of a test. That also is a number to help us understand how sensitive is our test in detecting difference. If the power of test is high, that means your test is more likely to detect difference. Okay, so that's how we define the power of a test. Okay, when null hypothesis is not true, you reject it, right? Or alternative hypothesis is true, and you support it. Okay, and it is actually related to sample size calculation. And I'm not going to go through the explanation of how that we get that formula. If you have the Pagano's book, I think Pagano's book explained a little bit about how they derive that formula. I'm going to just explain to you this formula, right? Now, so we have alpha, which is the level of significance for the test, right? Usually at 5%. And we have beta. Beta is related to the power of a test. Usually when we do hypothesis testing, people like to see a power of a test to be 80% or higher, right? So if you are providing power, you can find the beta right away. If I want my test to have power 80%, the beta will be what? 20%, right? Because 1 minus beta is the power, okay? If I want my test to have 90%, then the beta will be 10%, okay? So given alpha and given beta, I'll be able to figure out these z-score in this formula, right? Z of alpha and z of beta. These are z-scores such that the right tail area is these, okay? Also, if I know the standard deviation of the distribution. And plus, if I know the effect size that I want to detect. For instance, I want to see whether this drug can help me to reduce the cholesterol level by 10 units, okay? Then that 10 unit is the difference that we like to test. So put that 10 units here. Okay, so what you do, you put in z-score based on the alpha and z-score based on the beta and put in the standard deviation and the effect size squared. That's the sample size you need, right? In order to achieve that goal for power, 1 minus beta. Okay, now in some research, you may not have any pilot study done. Now for that situation, oftentimes people specify the effect size in terms of number of standard deviation. So I want my test to be able to detect 1 standard deviation, so make this one sigma. So sigma and cancel, you only have z alpha plus z beta squared. Okay? If I want my standard deviation to be half of a standard deviation, then this thing will be half of a standard deviation, 1/2 sigma. So sigma cancel, you have 1/2 in the denominator. So instead of saying that, I can actually have a formula like this. If I want my standard deviation, the effect size to be half of the standard deviation, then I have this delta at 1/2. And I know sigma and sigma always cancel, right? So how many standard deviation you want the effect size to be, just specify that here for the delta, and you get another set of formula. That is, if you don't have standard deviation information, but you specify your effect size and turn out number of standard deviation. Okay? I hope that makes sense, right? So this is the formula for calculating a sample size. Now, this is for one-sided tests. If you do two-sided tests, the difference is this term here. You're going to use a z of alpha over 2 instead of z of alpha. That's the difference. Okay? The rest of them the same. Likewise here. Okay? So let's look at an example. The goal is to test whether there's the average, maybe, well, 70, I can't remember exactly what, maybe the average pulse rate, right, for a certain population is different from 70 or not, okay? Want to test at a 5% level of significance. I want to test to have 90% power to detect a 5-unit difference, okay, in terms of average pulse rate. And if I have an estimate for the standard deviation of pulse rate that is 15, I got this information, I'll be able to calculate sample size, right? This is a two-sided test, okay? So this will be my formula. And I said the effect size is what? 5 units, right? So I put 5 units there. Standard deviation I know, and I have a power, it's 90%, so beta is 10.1, right? And 5% for alpha, then this will be 0.025, and you know that, right? 1.96. So what you do is just look up a standard normal table for this z alpha score, right? So alpha is 0.05, alpha over 2 is 0.025, so it'll be 1.96. So actually, you get z score 1.96, z alpha over 2 1.96, 0.01, z beta 1.28. Plug them into the formula, times standard deviation 15 divided by effect size 5 squared, you get 94.48. And so you need 95, right? So you just explain to the, maybe whoever, NSF or NIH, right, where you want to ask for grant, well, I need sample size of 95 because I want the test to have a power 90%, and I'm doing this test at the 5% level of significance, right? So I do need 95%, 95 people subject to involved in my study in order for me to achieve my research goal. Okay? Hope that makes sense, right? So this is about sample size determination. Okay? Let me see, what time is it? Any questions so far? Okay. I believe the concept probably it's making sense to you, right? But you just have to practice, right? Practice will make it work, right? So let's look at some examples. Right? Let me see. And plus, of course, you want to do your homework, right? Web assignment homework. And so let's look at this example. Same data that we had there, okay? We changed our question now. Before, we were trying to estimate the average performance index. Now we want to test whether the average performance index, heart performance index for this particular sample population is less than 7 or not. So we took a sample of 9 subjects, and let's say I found the mean and standard deviation. So I want to test this hypothesis. What kind of test? Since we have sample size 9, you cannot use z-test. And in fact, just forget about z-test. When it comes to testing mean, do t-test only, right? Although textbook mentions z-test, but that's not a practical one, right? And when you run the software, none of the software, most of the software, I shouldn't say none of the software, but most of the software only give you t-test. They don't bother give you a z-test, okay? So this is actually, usually we call this one sample t-test. And we're going to learn so many different tests. I wish you can remember these names because that's how you communicate with people, right? Let's say you don't want to do the test yourself in the future. You want a statistician to do this for you. You got to tell them, well, I like this t-test, right? And you probably also can help them because you know your data better, right? So when they say they want to use a t-test, one sample t-test, you will know whether it makes sense or not. And this is one sample t-test for me, all right? Now, there are actually so many t-tests you will find out in the future. There are other places you need to do t-tests for different purpose, right? So this is one sample t-test for me, okay? So in order to do that, you got to test hypothesis for normality, right? Check the assumption, I should say, right? So, well, you saw this p-value higher than 0.05 means normality is okay, right? So we want to state the hypothesis. What's the hypothesis? You got to have null and alternative, right? Actually, I usually use this H0 and HA, right? So null is mean is 7, always. Null is always equal to, right? An alternative reflecting the research question less than 7. Now, if you know your alternative, you want to change your null to this, that is fine, okay? They just have to be complement to each other, okay? And what's the value of a test statistic? We are doing t-test, right? So t-test, that's the sample mean minus the mean under the null hypothesis. What is this number? That's this. This is the mean under null hypothesis. Okay, the value you're testing. Divide by the standard deviation over square root n. That's the formula. Standardizing the sample mean, okay, using null hypothesis. So mean was 6, and mean under null hypothesis 7. Divide by standard deviation 0.87 over sample size of 9. Okay, you get a number that is negative 3.45. Okay, that's your test statistic, t-test statistic. Okay, the order doesn't matter. The first one will be your sample mean. The second one is the mean under null hypothesis. If you flip it, you're going to get the wrong sign, right? That's not good. Okay, then after that, important number you want to get is, since this is a left-sided test, you want the area to the left of this. So it's negative 3.45. What's the area to the left of it? It's kind of hard to see, right? Now, if you use Pagano's book, let me see, Pagano's book actually gives you right tail area. Degrees of freedom for this is 8. Right tail area 8, we have 3 point something. This is chi-square, I'm sorry, right? Degrees of freedom 8, 3 point something, 3.45. 3.45 is in between 3.35 and 5.04. And their tail area is between 0.005 and 0.0005, right? So if you use a table, this tail area here is actually also your p-value is in between 0.0005 and 0.005. So that is less than 0.05, right? If you use a t-table, you can draw your conclusion. A p-value less than 0.05, you reject null hypothesis, right? What's the decision rule? Since the alpha level is 5%, this problem, did I say that? I think I didn't say that, right? But in any situation, if it's not mentioned, that means 5%. That's pretty much standard, right? So you will reject null hypothesis if p-value is less than 0.05, which this is the alpha. Okay, and you'll find out in the future, we're going to learn so many different tests, and the decision rule always the same. Reject null hypothesis if p-value less than alpha, less than level of significance you use for the test. Okay, so from here you can draw a conclusion, right? You want to say that since p-value is less than 0.05, we reject a null hypothesis. So we're going to conclude that there is sufficient evidence to support the alternative that the average heart performance index for this population is statistically significantly less than 7. Okay, that's a conclusion you want to draw. Okay, that's a proper conclusion, more complete, right? So I'd like to see that in your homework too, making that kind of statement. Okay. Well, I have this note actually from last year. Maybe this is what I wrote. I should have typed them, right? There is sufficient evidence to support the alternative that the average heart performance index is statistically significantly less than 7. That is at 5% level of significance. Okay? So that you conclude the analysis of t-test. Okay? Now, if you really want to calculate a more accurate p-value, right? There are several ways to do this. Let me see. We can use Excel, I believe, right? Let's say. Let me see if I can find the Excel worksheet here. Okay, Excel. So Excel, if I have a degrees of freedom, let's do t, right? T, you see you have a t distribution, t dot s, dis, t, okay? If you specify the value negative 3.45, next one is degrees of freedom, that was 8, right? And then cumulative distribution, yes, 1. Remember, if you use 1, it asks for cumulative. So that's 0.004347. So you got the p-value. This is a more exact p-value, right? What we got from a table was in between 0.0005 to 0.005, okay? This is more precise, okay? Great, excellent. Let me see. What time is it? Okay, wonderful. You may be curious how we do this with R Commander, right? So let's try R Commander. Where is R Commander? I thought I'd load the R Commander here. Oh, here, still here. I hope it's... this is not the one. Wow, where did I put it? Okay. That's going to be a problem. Let me see, right? It's not the... I thought I downloaded a version last time. Okay, anyway, I'm using an older version of R Commander. Oh, actually, it doesn't even have R Commander. Huh. Oh, my God. How come? Okay, let me do this. Let me try to download a version, okay, from my website. Oh, wow. Whoops, that's not the wrong one. Huh? Which one? Not do this. Okay. Save link as. Desktop. I gotta ask him not to remove this in the future. I don't know whether I can do that or not. Anyway, so why I'm doing this, let me explain the next thing. Okay, we haven't talked about sample size yet, so let's look at a more example on the sample size. We actually talked about it, but we need to see another example, I should say. Okay, so the same type of problem. Actually, we want to look at this is about weight reduction. All right, so you're conducting a research, and the goal is to check whether a particular treatment help you to reduce weight or not. Right, so you have a group of subjects participating in the study, and you want to see average weight reduction is significant or not. Okay, so you want to perform a test at 5% level of significant. You want a test at has 90% power. Okay, and to detect a treatment that is different by or reduction by 10 pounds. Okay. And the weight reduction measure from the subject has a standard deviation of 30. So these are information given. Okay, and you try to make use of these information to maybe come up with a sample size. So when you read this information probably from your pilot study. Okay. And based on the pilot study, you try to calculate the sample size to justify your research, right? The number of subjects that you want to use for your research. So alpha is 0.05, beta be 1 minus 0.9, right? Be 0.1 because power is 90%, right? So beta will be 1 minus power, right? Power is 1 minus beta, beta is 1 minus power, okay? So you got to find out what is z of 0.05 and 0.1. You need that in the chart, in the formula. And this is 1.64 or 1.645. If you do interpolation, I think while you're doing practice, you've done that, right? And Z of 0.1 is 1.282. Let me just double check on that, right? This is using a Pagano's book. If you want to point 5, you have 0.051 and 0.049, right, in between 1.645, right? For a tail area, 0.1 is here, right? Actually, it's here, right? So you have tail area, Z score 1.28, right? I think I have probably used a software now to give me a more precise number, or some table actually give me one more decimal place. But anyway, so I got these T-scores. If you like to, you can actually just, if your table only give you 2 digits, you can just use a 2-digit if you want. Okay. So your sample size will be 1.645. That's from Z alpha, and plus 1.282. Okay. And time, standard deviation, and divide by effect size you wish to detect, and square this number. Okay. So you get a number that's 77.07. If you round up to 78, that would be the sample size you need. Okay. Okay. That's one-sided test, right? The next one is a two-sided test. Next example. If you need to do a two-sided test, okay, the difference will be the alpha 0.05, but you need the alpha over 2 for that Z-score 0.025. So your Z of alpha over 2 is Z of 0.025, which is 1.96 after you've done a lot of this confidence interval testing hypothesis with Z-test. Okay. And of course, beta will be 0.1, just like the one we had before. Okay. And so to do this problem, sample size will be 1.96 plus 1.282 time standard deviation 30 over 10, right? And square this, you get 42.03, rounded to 43. So that's it. Okay, that's the answer. Okay. Make sense? Okay. Now, like I say, in some study, this may not know. You don't know the standard deviation, right? So if I ask you to calculate the sample size, so the test has a 90% power to detect the treatment difference that is half a standard deviation. You want a test to have 90% power to detect half a standard deviation difference, right? Then what should you do then? Then you will have same score put the 1/2 there and square. That will be your sample size, right? You don't need the sigma anymore. How many standard deviation you wish to take as a effect size? Just put that number in the denominator. So if I wish to detect one standard deviation difference, put a 1 here. If I want to detect 2 standard deviation difference, put a 2 here. Okay. The higher the standard deviation you want to detect, the smaller the sample size you need. Because if the difference is very big, you don't really need a lot of data. You can find that difference, right? If you want to take a minor, very small difference, then you need a lot of data to help you to see that difference. Okay, so I hope that makes sense. Okay. Any question? Do you have any question? Okay, I believe with this, I think you can do your assignment, the springboard assignment. Okay. And for springboard assignment, for those questions that you can actually answer with the R commander, you're going to do R commander. There are a few questions that you have to do it by hand, like a sample size calculation.